Hello students, quick question. Have you ever tried using a magnifying glass to burn paper with sunlight? Admit it, at least some of you have. Or maybe you've seen how a projector can throw a sharp, bright picture onto a wall in your classroom. Behind both of these cool tricks lies the science of lenses. But here's the secret. Before we can do the big stuff like solving lens formula problems or tracing ray diagrams, we need to learn the alphabet of lens optics. Just like you can't spell words without knowing letters, you can't understand lenses without knowing their key terms. Hello students. Have you ever used a magnifying glass to burn paper with sunlight, or maybe noticed how a projector throws a sharp image on a wall? Behind these everyday wonders are some simple but very powerful terms in lens optics. Think of these terms as the alphabet of lenses. Without learning them, formulas and diagrams will feel like reading in a language you don't understand. For instance, the lens formula 1 by f equals 1 by v minus 1 by u only makes sense if you actually know what f, v, and u stand for. So let's start with the very first letter of this alphabet, the optical center. By definition, the optical center is the point O at the geometric center of the lens. And here's its amazing property: any ray that passes through this point travels straight without bending at all. We say the ray emerges undeviated. In symbolic form, delta theta equals 0 for a ray through O. In plain words, deviation is 0. Now let's bring in a real-life example. Imagine shining a laser pointer through the exact center of a lens. Instead of bending like rays usually do, the laser just keeps going straight. It's like having a VIP pass at a concert. While everyone else gets pushed and redirected, the VIP walks directly to the front row without any disturbance. So remember this golden rule: rays through the optical center travel straight. This one fact will save you a lot of time while drawing ray diagrams and solving problems. Alright students, now that we've met the optical center, let's move on to the next big term in our lens alphabet, the principal axis. By definition, it's the straight line that joins the optical center O with the two centers of curvature, C1 and C2. Think of it as the main highway running through the lens. All the important action happens in reference to this line. Why is it so important? Because it serves as the reference line for every single construction and ray diagram we draw. Without it, our diagrams would look like random doodles with no sense of direction. Now comes a very handy ray law. Any ray that is parallel to the principal axis will, after refraction, pass through the focus F in a convex lens. This is one of the golden shortcuts in ray diagrams, easy to remember and super useful. Let's connect it to real life. Imagine parallel sunlight rays coming down to Earth. If you pass them through a convex lens and place a paper at the focus, all those rays gather and burn a neat little hole in it. Many of you might have tried this trick during summer holidays, and yes, that's the principal axis and its ray law in action. So remember, the principal axis is not just a line in a diagram, it's the backbone of lens optics. Parallel rays obey it faithfully, and without it, lenses wouldn't know where to bring light together. Alright students, time to meet one of the most important stars in lens optics, the principal focus. Let's start with a convex lens. If rays of light come in parallel to the principal axis, they all bend inward and meet at a single point on the axis. That point is called the focus, and it's where the magic of convergence happens. Think of it like friends agreeing to meet at the same cafe. No matter where they come from, they all end up at the same spot. Now switch to a concave lens. Here, the rays don't actually meet. Instead, they spread apart as if they are running away from each other. But if you trace those diverging rays backward, they appear to come from a single point on the axis. That point is also called the focus, but this time it's a virtual focus. You could say it's like friends who promised to meet but never showed up, they only seem to have had a meeting spot. Symbolically, we represent two foci, f1 and f2, one on each side of the lens. And the distance from the optical center O to the focus f is what we call the focal length, written as f equals of. Real life? A convex lens focuses sunlight at its focus, perfect for starting a fire on a dry leaf. A concave lens, on the other hand, spreads light rays out, which is why it's used in spectacles for short-sightedness. So remember this, convex lenses bring rays together at the focus, concave lenses send them apart but make it look like they started from a focus behind the lens. Alright students, time to meet the last key term in our lens alphabet, the focal length. By definition, the focal length is the distance between the optical center O and the principal focus f. In symbols, we write it simply as f equals the distance from O to f, short and sweet. Now, why does this matter so much? Because the focal length tells us how strongly a lens bends light. A shorter focal length means the lens bends rays more sharply, like a strict teacher pulling students quickly into line. A longer focal length means gentler bending, more like a friendly teacher who lets you stroll in slowly. Here's the general formula we use all the time, 1 by f equals 1 by v minus 1 by u. Where f is focal length, v is the image distance, and u is the object distance. This is the golden relation that helps us solve almost any lens problem. Let's try the example here. Suppose f is 15 centimeters and u is minus 20 centimeters. Substituting into the lens formula, we find v equals 60 divided by 7, which is about 8.57 centimeters. That means the image forms at 8.5 centimeters on the other side of the lens. And here's the real-life connection. A projector lens has a longer focal length to spread the image large across a screen, while a magnifying glass has a short focal length to bend light strongly and make small things look huge. Same principle, different uses. So, remember, focal length is not just a number, it's the personality of the lens telling us how hard it works to bend light. Alright students, let's add two more terms to our lens alphabet, the aperture and the center of curvature. First, the aperture. This is simply the effective diameter of the lens through which light rays actually pass and get refracted. The bigger the aperture, the more light the lens captures. That's why camera lenses with large apertures can take bright, sharp photos even in dim light. More light in, better picture out, simple. Now, on to the centers of curvature, marked as C1 and C2. Remember that a lens is made from two spherical surfaces. If you extend those surfaces into full spheres, the centers of those spheres are called the centers of curvature. From these, we define the radius of curvature, which is the distance from the optical center O to either C1 or C2. Symbolically, R equals the distance from O to C. Here's an interesting connection. For a thin lens, we can approximate the focal length as f is about equal to r divided by 2. So if you know the radius of curvature of the lens surface, you can get a pretty good estimate of its focal length. Think of it this way, the aperture decides how much light your lens grabs, while the radius of curvature and the focal length decide how the lens bends that light. Together, they're like the width of a cricket bat and the angle at which you swing. One controls how much you hit, the other where the ball goes. Alright students, time for a quick revision. Let's go over the key technical terms of a lens one last time. Think of this as flipping through your flashcards before the big test. First up, the optical center O. Remember, this is the magical point in the middle of the lens where a ray of light passes straight through without bending. Symbolically, delta theta equals 0. In real life, it's like a VIP guest walking through a crowded hall, no detours, no checks, straight to the other side. Next, the principal axis. This is the straight line joining the optical center O with the two centers of curvature, C1 and C2. It's the main reference line of the lens, just like the main road in a city map. Every ray diagram you draw depends on this road. Now, the principal focus F for a convex lens, it's the point where rays parallel to the axis meet. For a concave lens, it's the point from which rays appear to diverge. So convex gathers the party, concave pretends there was a party behind the scenes. Then we have the focal length F. This is the distance from the optical center O to the focus F. The key relation to remember is 1 by F equals 1 by V minus 1 by U. Without this formula, lens problems are like cricket without a ball. The game just can't be played. Finally, the aperture and radii of curvature are. The aperture tells us how much light the lens can capture, bigger aperture, brighter image. The radii of curvature define the actual geometry of the lens and for thin lenses even linked to the focal length. So there you go, optical center, principal axis, principal focus, focal length, aperture and curvature. Master these, and the entire world of lens optics becomes a lot less blurry, pun fully intended.